Now let's talk about the second topic of this lecture, and that is the entropy of chemical reactions. Oh, finally, as chemists, we're going to talk about chemistry. Because entropy is a state function, delta S is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. Now note that this does not have any deltas. Let's contrast and compare there with, for example, the standard enthalpy of a reaction is the standard enthalpy of formation of the products minus the standard enthalpy of formation of the reactants. On the other hand, now we have the entropy, and let's make this a standard entropy of the reaction, is just now the entropy, the absolute entropy of the products minus the absolute entropy of the reactants. And these you can determine absolutely. There's nothing relative about them. You don't have to refer them to a standard state because the entropy of the products and reactants is 0 at 0 Kelvin. Now, what exactly standard state? Standard states, well, you're free to describe a standard state. So let's describe a standard state for a chemical reaction to be 1 bar. Now, bar is a measure of pressure and is very similar to the atmosphere pressure unit that we've talked about in introductory chemistry and used so far. But it's a little different, just enough different to make a difference. So 1 atmosphere is 1.01325 bar. So an atmosphere is a little bit more than a bar. If we're real physical chemists, we're going to use 1 bar as a standard state. But if we're sort of introductory level students, we can use 1 atmosphere. Now the point is that the standard, see that 0 means standard entropy. So although we don't have to calculate standard entropies because we have an absolute value, nonetheless we'll define an entropy change as standard as 1 bar. So the entropy of 1 bar of the products minus entropy. If we define our standard state not to be 1 bar but 1 atmosphere, then the standard entropy change may very well be different because we have a different standard state. So different standard states or different temperatures or volume changes, what you can do is if you're not at the standard state, you convert to the standard state, both the reactants and products, and then you can calculate the standard entropy change. And here are the 2 important equations one uses to calculate entropy changes going from one state to another. One state to another. This is the entropy change, heat capacity times the natural log of the final over the initial temperature, or the entropy change is the minus nR log of the final pressure over the initial pressure. Now just to show you that this is going to make a difference, let's do this example. What's the difference in the standard entropy of formation of 1 mole of gaseous water if the standard pressure of 1 atmosphere is used instead of 1 bar? Assume all gases are ideal gases. So for example, if you say that delta S0 is some number, that doesn't mean anything unless you specify what the standard state is. So you must specify what standard state is, because this is meaningless unless you say what the standard state is. If you have a different standard state, you'll get a different entropy for the reaction. So the problem says, well, we're physical chemists, so we are going to use 1 bar. But suppose somebody used 1 atmosphere instead, then this delta S0 will be different if the 0 refers to 1 atmosphere. And let's actually just calculate that, what the actual difference in the standard enthalpy of formation will be. So you remember, so what chemical reaction are we talking about? We're talking about the standard entropy of formation. So remember, entropy of formation, you take of gaseous water. So we're going to write down the reaction for the entropy of formation of gaseous water from its elements. And this goes to H2O gas, and this is a gas also. All right, so there's a chemical reaction, and what we're going to assume here, let's say this is, say, 1 atmosphere, and this is all 1 atmosphere. So this is the entropy change, standard entropy change when using 1 atmosphere. And what we want is the same reaction, sorry, that's not O. What we want is the same reaction going here, H2O, where this is 1 bar, and these all here are 1 bar. And the entropy change here, delta S0, this will be at 1 bar. So we want to see how the standard entropy will change when you use 1 bar versus 1 atmosphere. So how do you think we're going to do this? Well, we're going to write a thermodynamic cycle. First, we'll take the reactants in 1 atmosphere and we'll take those to 1 bar, from 1 atmosphere to 1 bar. And that will give us some entropy change. And how do we do that? Well, here we go, entropy change. Right there, see, pressure change, we can calculate the entropy change. So far so good, so call this delta S1. Then here's the standard entropy. Now we got the products. Let's take the products down to 1 atmosphere. Call this delta S3 for the 1 to 3rd step. So now we take the product from 1 bar to 1 atmosphere. A pressure change, which we can calculate the entropy change there. So the problem asks, what is the difference between these two quantities when you calculate it this way versus this way? It's a thermodynamic cycle, so that delta S, the standard entropy of that reaction at 1 atmosphere, will be equal to delta S1, taking it up to 1 bar, plus standard entropy change of the reaction at 1 bar, plus delta S3. So entropy is a state function. So the entropy change going from here to here is equal to the entropy change that plus that plus that. And that's just what we've written. The problem asks to what's the difference in the standard entropy of formation of these two processes. Didn't really say what minus what. So let's do say delta S0 at 1 atmosphere. Standard entropy when you have a standard state of 1 minus the standard entropy when you have a standard state of 1 bar. That is equal to delta S1 plus delta S3. Let's look at delta S1. What are you doing with delta S1? All right, so here we're taking a gas here at 1 atmosphere, hydrogen, putting it 1 bar. And here we're taking a half a mole of this gas at 1 atmosphere and putting it at 1 bar. And we said we can calculate those changes by this, or those entropy changes by this equation here. And we want to do it 1 mole of gaseous water. So we have 1 mole of this being produced. That means we have 1 mole of this and a half a mole of this. So delta S1 will be, let's do the hydrogen first, 1 mole. No, I have to keep, what do you think? Should I have unit? All right, I'll put units in. 1 mole. And note that's a minus sign. There was a minus sign here. Don't forget that minus sign there. N, R, 8.314 joule per mole Kelvin times the natural log of the final pressure, 1 bar, over the initial pressure, 1 atmosphere. We've done hydrogen. We took it from 1 atmosphere to 1 bar. Let's do oxygen. That'll be the second term that contributes to delta S1 minus a half mole. I'll omit the units for this one. 8.314 times the natural log of 1 bar over 1 atmosphere. That's delta S1. That's that one. Let's look at delta S3 plus delta S3. That's for that second step. Here we're taking 1 mole of water at 1 bar and converting that to 1 mole of water at 1 atmosphere, a pressure change. So delta S3 will be 1 mole of water. Don't forget that minus sign. 1 mole of water times 8.314 joule per mole Kelvin times the natural log. Our final pressure now is 1 atmosphere. Our initial pressure is 1 bar. So we started at 1 bar and now we're going to 1 atmosphere. Okay, we can pull these things out. Let's see, this is minus 1. Pull this out. Well, before we do that, let's make this a little easier here. Sometimes it's useful to do manipulations algebraically before you actually pull out your calculator and do something. So let's just do that. So here, there's 1 bar, 1 atmosphere, there's 1 atmosphere, 1 bar. Let's flip this over. And so let's make this minus natural log of 1 bar over 1 atmosphere. So we got natural log 1 bar atmosphere, 1 bar atmosphere, 1 bar atmosphere. So now we can combine all these terms. So, well, let's try to do it here, see if we have enough room. All right, so natural log of 1 atmosphere over 1 bar. So we pull that out. Let's pull out R, 8.314 And now what we're left with is minus 1, minus 1/2. And now I've got to be careful here. There's a negative, and that's a negative. That cancels out the negative, so this will be plus 1. Slight mistake here. I've changed this to 1 bar per atmosphere. So let me just rewrite this as 1 bar over 1 atmosphere. This is 1/2. We have, and don't forget the minus sign here, 0.5 mole. Just rewrite everything here. 8.314 joule per mole Kelvin times the natural log of 1 bar divided by 1 atmosphere. It'd be nice if we had the same units here so we can cancel that out. Let's just see if we can get that. It should be chemical reactions. Here we go. No, not quite yet. There we go. 1 atmosphere is 1.01325 bar. So we can substitute 1 atmosphere for that. So this is minus 0.5 mole. 8.314 joule per mole Kelvin times the natural log of 1 bar, and we said 1 atmosphere is 1.01325 bar. Finally, we can cancel those things out. We put all this into our calculator and we get 0.0547 joule per Kelvin. Note that this number is less than 1, so the logarithm will be negative, which will cancel out that. So, and what was this for? This was for the standard enthalpy change when we used 1 atmosphere minus the standard entropy change when we used 1 bar. So this shows that depending upon what you define as the standard state, you'll get a different number, because the difference here, if they were the same number, you get 0, but in fact it's a small number, but nonetheless significant number. If you are working in research and you publish some information about enthalpy or entropy or some thermodynamic quantity to standard state, make sure you always specify what the standard state is. Okay, that's it. I hope you enjoyed listening.